You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Domain 3 of cloud security provides the technical backbone for safeguarding the platforms, networks, compute resources, and supporting services that make up the modern cloud. If we imagine the cloud as a vast digital city, Domain 3 represents the infrastructure, the streets, buildings, and utilities, without which no higher-level applications could function. Its purpose is to ensure that the underlying environment is not only functional but also resilient, trustworthy, and capable of supporting secure operations at scale. For learners, this domain ties together concepts of platform governance, workload protection, and infrastructure hardening, providing a comprehensive foundation. Understanding Domain 3 is not just about memorizing controls, but about appreciating how layers of defense interact to form a secure ecosystem. By the end of this material, it becomes clear that effective cloud security is built from the ground up, and weaknesses at this level can undermine every other safeguard above it. The scope of Domain 3 is broad because it encompasses virtualization, compute workloads, containerized environments, serverless execution models, and all the supporting infrastructure that binds them together. Virtualization provides the abstraction layer that allows multiple systems to run on the same hardware, while compute workloads are the virtual machines or instances carrying out processing tasks. Containers and orchestrators introduce portability and agility, but also create new layers of governance. Serverless functions represent an even higher abstraction, where developers focus purely on code and events without managing operating systems or hosts. Each of these technologies has distinct security considerations, yet they must be managed under a unified strategy. Supporting infrastructure includes not only the compute and storage, but also the networks, gateways, and administrative services that tie them together. By treating the scope holistically, professionals recognize that securing cloud infrastructure is a multi-dimensional challenge requiring coordinated, layered defenses. Management plane security lies at the heart of platform defense because it governs the interfaces through which administrators configure and control cloud resources. Unlike traditional systems where access might be limited to physical consoles or private networks, cloud platforms expose powerful management APIs accessible from anywhere on the Internet. This creates both convenience and risk. Protecting the management plane involves ensuring that identities are properly authenticated, privileges tightly controlled, and interfaces monitored for misuse. For example, enabling multi-factor authentication for administrators significantly reduces the risk of compromise through stolen passwords. Likewise, restricting API keys and enforcing role-based access help minimize potential abuse. Attackers often target the management plane because a single breach can unlock broad control over resources. Therefore, this layer must be treated as a crown jewel, with controls such as network restrictions, audit logging, and just-in-time elevation reinforcing its resilience. Without management plane security, the foundation of the entire platform remains vulnerable. Compute security provides another essential layer of defense, focusing on the virtual machines or instances that perform the heavy lifting of workloads. Security begins with baseline configurations, ensuring that operating systems are hardened against common vulnerabilities. This includes disabling unnecessary services, applying secure defaults, and aligning builds to recognized benchmarks. Patching cadence is equally important, as unpatched systems are prime targets for attackers exploiting known flaws. Many organizations now automate patching processes to maintain consistency across elastic fleets of instances. Hardened images, sometimes called gold images, serve as trusted starting points for deployments, embedding secure configurations from the outset. By using these pre-approved templates, organizations reduce variability and risk. Compute security may seem straightforward, but in practice, the scale and dynamism of the cloud demand careful orchestration. A lapse in configuration or delayed patch can propagate across hundreds of workloads, turning small oversights into significant attack surfaces for adversaries to exploit. Container platform security introduces unique considerations because containers are lightweight, fast-moving, and highly dependent on orchestration tools like Kubernetes. At the platform level, governance is required to ensure that orchestrators enforce strict policies over how workloads are scheduled, networked, and scaled. Node hardening is crucial because vulnerabilities in underlying hosts can compromise the entire cluster. Image provenance adds another critical factor. Every container should come from a trusted source, verified through signatures or registries to prevent tampered or malicious images from entering the environment. Runtime controls further extend security by monitoring active containers for suspicious behavior, such as unexpected network calls or privilege escalation attempts. Unlike traditional servers, containers are ephemeral, meaning they can spin up and down in seconds, so visibility and control must be automated and continuous. By combining governance, hardening, provenance, and runtime monitoring, organizations can achieve layered defense in containerized ecosystems, preventing small missteps from cascading into systemic vulnerabilities. Serverless execution models challenge traditional security practices by abstracting away the underlying host. In serverless environments, developers deploy code that runs in response to specific events, such as a file upload or an API call, without managing servers directly. This model offers efficiency but shifts the security focus to event sources, execution roles, and dependencies. Least privilege execution roles ensure that each function has only the access it needs, limiting potential damage if compromised. Dependency management becomes critical because serverless functions often rely on external libraries or packages, which may introduce vulnerabilities. Organizations must track and validate these dependencies to prevent supply chain risks. Event source configuration is equally important, as improperly scoped triggers could allow unauthorized invocations or denial of service conditions. While serverless reduces administrative burden, it does not eliminate responsibility. Instead, it redefines it, requiring careful attention to the code, the events that activate it, and the privileges it consumes during execution. Network security within Domain 3 is not simply about firewalls. It is about designing secure pathways for data to flow within and across cloud environments. Traditional segmentation still applies, separating workloads into distinct virtual networks to reduce exposure. Microsegmentation adds finer control, allowing administrators to define policies at the level of individual workloads or services, limiting lateral movement. Ingress and egress controls manage traffic entering and leaving the environment, while east-west traffic inspection focuses on communication within the cloud itself, such as between application tiers. Each of these layers contributes to a defense-in-depth strategy. For example, microsegmentation can prevent an attacker who compromises one workload from freely moving across an environment. Cloud-native tools like virtual network appliances, distributed firewalls, and service meshes provide the technical means to enforce these controls. By viewing the network as both a connective tissue and a potential attack surface, organizations can architect security directly into the fabric of their platforms. Identity integration plays a decisive role in administrator access control, tying together authentication, authorization, and federation across platforms. Cloud environments often integrate with enterprise identity providers, allowing centralized control over who can access resources. Multi-factor authentication serves as a critical safeguard, adding an extra barrier beyond passwords. Least privilege principles ensure that even administrators receive only the access required for their roles, preventing over-entitlement. Federation further extends security by enabling single sign-on across multiple services, reducing password sprawl and improving monitoring. For example, federated identities may link an employee's corporate account to their cloud administrative role, ensuring that access follows organizational policies and can be promptly revoked when employment ends. Without strong identity integration, management plane security collapses, as attackers could exploit weak or mismanaged accounts. Thus, identity functions as the key to every other control in Domain 3, anchoring trust and ensuring accountability across complex, distributed infrastructures. Secrets management is a perennial challenge in cloud environments, where credentials, keys, and tokens proliferate across applications and platforms. Storing secrets in plain configuration files or hard-coding them into applications creates serious risks, as attackers who gain access to source code or logs may harvest sensitive credentials. Centralized secrets management systems mitigate these risks by providing secure vaults where credentials are stored, rotated, and accessed only under strict auditing. Automated rotation reduces the likelihood of long-lived secrets being compromised, while retrieval policies ensure that applications fetch secrets only when needed. For instance, a web application might retrieve a database password dynamically from a vault at runtime, rather than embedding it in its configuration. Secrets management also supports regulatory compliance by documenting how sensitive credentials are handled. By centralizing, automating, and auditing secrets, organizations reduce the human errors and oversights that so often lead to breaches in cloud environments. Infrastructure as Code, or IAC, represents both an opportunity and a challenge for cloud security. With IAC, infrastructure is defined and deployed using code templates, enabling consistency, repeatability, and automation. However, insecure templates can propagate vulnerabilities at scale. Governance over IAC templates ensures that only reviewed and approved configurations are deployed, reducing the risk of misconfigurations. Pre-deployment validation tools can scan templates for insecure practices, such as open security groups or weak encryption settings, before resources are launched. Drift detection adds another safeguard, continuously checking whether live systems match the desired configurations and alerting when deviations occur. By treating infrastructure as code, organizations gain efficiency, but must also adopt development-like practices of testing, peer review, and version control. When applied responsibly, IAC not only accelerates operations but also enhances security by embedding best practices directly into the deployment pipeline, turning infrastructure management into a controlled, auditable process. Software supply chain security has become an urgent concern as organizations depend on complex ecosystems of code, packages, and artifacts. In cloud environments, these components underpin everything from application runtimes to infrastructure services. Verifying sources ensures that artifacts come from trusted repositories rather than tampered channels. Bills of materials, or SBOMs, provide transparency into what components are included in builds, helping identify vulnerable dependencies. Signatures and integrity checks confirm that artifacts have not been altered since creation. For example, an unsigned or unverified container image could conceal malicious code, making provenance checks essential before deployment. Supply chain compromises can have cascading impacts, allowing attackers to infiltrate environments at scale. By applying rigorous verification, organizations create barriers that prevent poisoned code from entering production. This practice not only protects immediate operations, but also strengthens resilience against systemic threats, where the compromise of a single upstream provider could ripple across countless dependent systems. Logging and telemetry provide the visibility necessary to detect, investigate, and respond to threats in cloud infrastructure. Control plane logging captures administrative actions, such as API calls or configuration changes, while data plane logging records activity within workloads, such as network flows or file access. Together, these sources allow security teams to reconstruct events and identify suspicious behavior. Telemetry, which includes metrics and performance indicators, supplements logs by showing patterns over time, such as spikes in traffic or unusual resource consumption. Collecting logs is not enough. They must be stored securely, correlated across systems, and analyzed in near real time to be effective. For example, a sudden increase in failed login attempts may indicate a brute force attack, while unusual east-west traffic could suggest lateral movement. In cloud environments, logging and telemetry also support compliance, providing evidence that controls are operating effectively. Ultimately, visibility transforms unknown risks into detectable signals, forming the foundation of operational assurance. Vulnerability management remains a cornerstone of security, ensuring that weaknesses across hosts, containers, and services are identified, prioritized, and remediated before attackers exploit them. Discovery involves scanning systems for known flaws, but in cloud environments where resources are elastic, this must be automated to capture new instances as they appear. Prioritization is equally important, focusing limited resources on vulnerabilities that pose the greatest risk based on severity, exploitability, and exposure. Remediation involves patching, configuration changes, or even decommissioning vulnerable components. For example, a high-severity container runtime flaw might require immediate updates across an entire cluster. Cloud-native vulnerability management tools integrate directly with platforms, offering continuous scanning and automated ticketing. Without this discipline, organizations fall behind the curve, leaving exploitable gaps that adversaries eagerly target. By making vulnerability management proactive and integrated, Domain 3 ensures that defenses evolve at the pace of threats rather than lagging dangerously behind them. Resilience engineering emphasizes designing systems to withstand and recover from failures, recognizing that no infrastructure is invulnerable. Redundancy ensures that critical components have backups, whether through multiple instances, regions, or providers. Failover mechanisms automatically shift workloads when primary systems fail, reducing downtime. Automation extends this resilience by detecting failures and initiating recovery without human intervention, speeding response times. For example, a resilient database service might replicate data across regions and fail over transparently if one becomes unavailable. This engineering mindset moves beyond prevention to embrace continuity, ensuring that systems remain available even under stress. In cloud environments, where elasticity and distribution are core features, resilience engineering transforms potential fragility into robustness. By treating availability as a security concern, Domain 3 aligns operational reliability with trust. Users, regulators, and business leaders alike expect that critical services will remain functional, even in the face of unexpected disruptions or targeted attacks. Backup and recovery strategies round out the protective measures of Domain 3 by ensuring that both data and platform states can be restored after loss or corruption. Backups must extend beyond user data to include configurations, infrastructure templates, and metadata necessary to rebuild environments. Testing recovery procedures is just as important as performing backups, as untested plans often fail under real-world pressure. For example, an organization may back up virtual machine images, but discovered during an incident that dependencies like network configurations were not included, delaying restoration. Cloud-native backup tools offer advantages such as regional replication and automated scheduling, but they must be aligned with organizational policies for retention and compliance. Effective backup and recovery strategies protect not only against accidental deletion but also against deliberate attacks like ransomware. By embedding resilience into recovery, organizations ensure that setbacks are temporary rather than catastrophic, preserving confidence in their infrastructure. Edge and hybrid architectures extend the security perimeter by bridging cloud platforms with on-premises systems, private links, and distributed gateways. Edge computing pushes workloads closer to users or devices, improving performance but also creating new points of exposure. Hybrid architectures connect private data centers with public clouds, demanding consistent security policies across diverse environments. Gateways serve as critical choke points where access must be controlled, encrypted, and monitored. Private links provide secure, dedicated pathways between systems, reducing reliance on public internet exposure. The challenge lies in maintaining consistency. Policies must be enforced across environments to prevent gaps that attackers could exploit. For example, an access control policy applied in the cloud but neglected on-premises could create an entry point for lateral attacks. Securing edge and hybrid deployments requires harmonizing controls, ensuring that security follows the workload wherever it resides, and extending Domain 3 principles across a truly hybrid ecosystem. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Baseline standards such as the Center for Internet Security Benchmarks and the Security Technical Implementation Guides provide organizations with a common language for hardening systems. These standards distill years of experience into prescriptive controls, such as disabling unnecessary services, enforcing password complexity, or limiting administrative accounts. Applying them to cloud workloads ensures that security is not left to chance or personal preference. In practice, aligning to benchmarks provides not only technical assurance but also evidence for regulators and auditors that systems are configured according to recognized best practices. For example, a virtual machine image built to CIS standards is far less likely to expose weak defaults than an ad hoc configuration. Standards also provide a baseline for continuous monitoring, as deviations can be quickly detected and corrected. By embedding these guidelines into build pipelines and deployment templates, organizations translate abstract principles into concrete, repeatable safeguards for their platforms. Patch orchestration is the discipline of managing software updates across sprawling, dynamic cloud environments. Unlike traditional data centers where systems may be patched in predictable windows, cloud workloads scale elastically, and tenants may share infrastructure. This raises the need for coordination, as maintenance must minimize disruption while ensuring vulnerabilities are quickly remediated. Orchestration involves scheduling maintenance windows, defining rollback plans in case updates break functionality, and verifying that patches apply correctly. Automation plays a crucial role, enabling thousands of instances to be updated without manual intervention. For example, rolling updates may patch subsets of nodes while keeping the system operational. Verification ensures that updates are not just deployed but effective, closing the intended security gaps. Without orchestration, patching can become inconsistent, leaving exploitable weaknesses. With orchestration, it becomes a controlled, predictable process that balances security, availability, and performance, ensuring that the organization maintains both resilience and compliance in a shared cloud context. Privileged access management addresses one of the most critical risks in cloud security: the misuse of powerful administrative accounts. These accounts, sometimes referred to as break-glass credentials, can override normal restrictions and must therefore be handled with extreme care. Best practice requires restricting who can use these credentials, ensuring they are invoked only under exceptional circumstances. Session recording provides visibility into what administrators do during elevated sessions, deterring misuse, and supporting forensic analysis if something goes wrong. Command auditing further strengthens accountability by logging every action, creating a record that can be reviewed and validated. For example, if an emergency required bypassing automated controls, privileged access management would document who used the account, when, and why. Without such controls, organizations risk both internal abuse and external compromise, as attackers often seek to escalate privileges after initial access. By rigorously managing privileged access, organizations safeguard their most sensitive pathways of control. Configuration management ensures that systems remain aligned with intended security postures, even as environments evolve. Cloud infrastructure is inherently dynamic, with workloads frequently spun up, modified, or decommissioned. Configuration management tools define a desired state and enforce it across resources, detecting and correcting drift whenever systems deviate. Automated reconciliation can reset unauthorized changes, maintaining consistency without human intervention. For example, if a firewall rule is altered to allow broader access than intended, configuration management systems can automatically restore it to the approved state. This discipline prevents configuration sprawl and ensures that security does not erode over time. Importantly, it also provides auditable evidence that systems are managed in line with policy, supporting both internal governance and external compliance. By embedding configuration management into operations, organizations transform security from a one-time effort into a continuous process, ensuring that resilience is maintained even in the face of constant change. Cloud workload protection platforms provide a unified set of controls to safeguard workloads across hosts, containers, and runtimes. These platforms integrate capabilities such as intrusion detection, vulnerability scanning, and runtime monitoring into a cohesive solution tailored for the cloud. Unlike traditional endpoint protection, CWPPs are designed to handle the elasticity and heterogeneity of cloud workloads, providing consistent visibility and defense regardless of where workloads run. For example, a CWPP might detect anomalous behavior in a container runtime, such as an attempt to escalate privileges and automatically block the action. The advantage lies in consolidation. Rather than relying on fragmented tools, CWPPs offer a single pane of glass for protecting diverse environments. They also integrate with cloud-native APIs, enabling scalable deployment and management. In doing so, CWPPs address one of the central challenges of Domain 3: how to maintain effective security across rapidly shifting, highly varied workloads in distributed infrastructures. Cloud infrastructure entitlement management has emerged as a specialized discipline for analyzing and controlling permissions in cloud platforms. In many organizations, identities accumulate excessive privileges over time as roles evolve or administrators apply broad permissions for convenience. CIEM tools analyze these entitlements, identify unnecessary or risky permissions, and recommend reductions to least privilege. For example, a developer account may have lingering administrative rights from a past project, creating unnecessary exposure. CIEM highlights such over-provisioning and can automate remediation. In cloud environments, where thousands of identities interact with countless services, manual review is impractical. CIEM provides the analytical layer to prevent privilege sprawl and reduce the blast radius of compromised accounts. By continuously assessing and right-sizing permissions, CIEM strengthens access governance and supports compliance requirements. It reflects the reality that identity, not just infrastructure, represents one of the most important control planes in cloud security. Key management underpins trust in cloud platforms, ensuring that encryption and digital signatures remain secure and reliable. Integrating hardware security modules, cloud-based key management services, and well-defined rotation policies ensures that keys are both protected and usable. Hardware security modules provide tamper-resistant environments for key storage, offering the highest assurance. Cloud key management services deliver scalability and integration, enabling organizations to manage large volumes of keys across services. Rotation policies prevent long-lived keys from becoming persistent liabilities, reducing the chance of compromise. For example, an encryption key used to protect storage buckets may be automatically rotated every 90 days, with applications updated seamlessly. Poor key management, by contrast, undermines encryption itself, as compromised or misused keys render protections ineffective. By embedding key management into platform governance, organizations create a foundation of trust that supports confidentiality, integrity, and availability across all workloads and services. Monitoring and alerting turn raw telemetry into actionable signals, aligning operational metrics with service-level objectives and failure modes. Metrics such as CPU utilization, request latency, or packet drops provide insight into both performance and potential security concerns. Thresholds define acceptable ranges, while alerts notify operators when systems deviate, enabling timely response. For example, an unexpected surge in outbound traffic might trigger an alert suggesting data exfiltration. Monitoring systems must be carefully tuned to balance sensitivity and noise, avoiding alert fatigue while still detecting meaningful anomalies. In cloud environments, integration with auto-scaling and orchestration adds further complexity, as metrics shift dynamically. Aligning monitoring with defined objectives ensures that alerts focus on protecting business-critical functions. This transforms monitoring from a passive activity into a proactive safeguard, enabling resilience and accountability. When designed effectively, monitoring and alerting embody the principle that visibility is the bedrock of secure operations. Backup scope in cloud environments must extend beyond user data to encompass the broader ecosystem that makes platforms functional. Backing up platform metadata, infrastructure templates, and configuration files ensures that environments can be rebuilt quickly and accurately. Images of virtual machines or container snapshots provide additional safeguards, reducing recovery times after disruption. Without such comprehensive scope, recovery efforts may fail despite having raw data, as critical dependencies are missing. For instance, restoring application data without the associated networking rules or identity configurations may render the system unusable. Tested backup strategies confirm that scope aligns with operational needs, identifying gaps before they matter. Cloud-native backup solutions simplify much of this process, but scope definition remains a human responsibility. By broadening the view of what constitutes critical data, organizations transform backup from a narrow data protection exercise into a holistic strategy for platform resilience and continuity. Cross-account or cross-subscription patterns help isolate environments, reducing the blast radius of potential breaches. By separating production, testing, and development into distinct accounts or subscriptions, organizations ensure that a compromise in one domain does not automatically cascade into others. Delegated administration allows central oversight while preserving boundaries, creating a layered approach to control. For example, developers may manage resources in a test subscription but have no direct access to production systems, preventing accidental or malicious actions. This model also simplifies compliance reporting, as environments are cleanly delineated. In multi-cloud scenarios, cross-account strategies become even more critical, as each provider's native boundaries must be aligned with organizational security models. By treating accounts as security perimeters, organizations create structural defenses that complement technical controls. This separation not only limits exposure, but also provides clarity and predictability, enabling faster incident response and more precise risk management. Compliance mapping connects platform controls to regulatory frameworks, ensuring that operations meet external obligations while producing evidence for audits and attestations. Rather than reinventing requirements for each regulation, mapping aligns existing controls to frameworks such as ISO 27001, NIST, or GDPR. This creates efficiency and reduces duplication of effort. For example, a logging system that records administrative actions may fulfill requirements across multiple frameworks simultaneously. Compliance mapping also facilitates reporting, enabling organizations to demonstrate adherence with tangible evidence. In the cloud, where shared responsibility blurs lines between provider and customer, mapping clarifies accountability. Providers may supply attestations for underlying infrastructure, while customers must document application-level controls. By organizing these relationships, compliance mapping transforms regulatory burden into structured governance. It shifts compliance from a reactive checkbox activity to a proactive practice that reinforces security, ensuring that platforms are not only operationally sound, but also demonstrably trustworthy. Cost-risk optimization acknowledges that cloud security decisions are not made in a vacuum, but must balance performance, redundancy, and expenditure against defined risk appetites. Adding multiple layers of redundancy may improve resilience, but also increase costs significantly. Conversely, minimizing spend could expose the organization to unacceptable downtime or data loss. Optimization requires understanding the business impact of different failure scenarios and investing accordingly. For example, a customer-facing payment system may justify multi-region replication despite higher costs, while an internal test environment may not. Cloud providers offer flexible options for redundancy and performance, but organizations must make deliberate choices aligned to their strategic priorities. Documenting these decisions ensures transparency and supports accountability. By framing cost decisions within a risk context, organizations align financial stewardship with security goals, creating a balanced approach that sustains both resilience and efficiency over time. Documentation practices serve as the connective tissue between design, operations, and assurance in Domain 3. Recording architecture decisions, configuration histories, and operational runbooks provides continuity across teams and time. For example, documenting why a particular encryption algorithm was chosen ensures that future staff understand the rationale and can evaluate its ongoing suitability. Change histories provide traceability, allowing investigators to reconstruct how a system evolved and when specific vulnerabilities may have been introduced. Operational runbooks ensure that responses to incidents or failures are consistent and repeatable. Beyond supporting daily operations, documentation provides auditors and regulators with tangible evidence that processes are deliberate and controlled. In cloud environments where automation reduces visibility into underlying infrastructure, documentation becomes even more important. It serves as the institutional memory that ensures consistency and defensibility, transforming ephemeral cloud resources into systems governed by clear, auditable intent. Continuous improvement closes the loop by embedding feedback from incidents, audits, and performance metrics back into security practices. Postmortems provide structured analysis of failures, identifying not just what went wrong but why it happened and how to prevent recurrence. Audit findings highlight gaps in compliance or governance, while metric trends reveal long-term patterns that may require strategic adjustments. For example, recurring misconfigurations detected by drift monitoring may indicate the need for stronger IAC governance or staff training. Continuous improvement transforms security from a static set of controls into a living program that evolves alongside threats and technologies. In the cloud, where change is constant, this adaptability is crucial. Organizations that embrace continuous improvement not only correct weaknesses but also strengthen resilience over time, ensuring that Domain 3 principles remain relevant and effective in the face of evolving demands. For exam preparation, the relevance of Domain 3 lies in recognizing platform threats, selecting layered defenses, and producing verifiable evidence that controls are functioning. Candidates must demonstrate an ability to understand how elements like identity, network, and workload protections interact to form secure platforms. They should also appreciate the importance of governance, documentation, and compliance evidence in making security defensible. Exam questions may focus on identifying appropriate controls, interpreting shared responsibility, or selecting best practices for securing cloud infrastructure. While technical knowledge is essential, the emphasis is equally on strategy, knowing not just how to implement controls but why they matter and how they are evaluated. This holistic understanding equips professionals to both succeed on the exam and translate knowledge into effective practice, ensuring that cloud platforms are not only technically secure but also auditable and resilient. In summary, Domain 3 integrates identity, network, compute, and governance controls into cohesive strategies that secure cloud platforms. It emphasizes not only hardening individual components, but also orchestrating them into resilient systems capable of withstanding threats and failures. The domain highlights the importance of baselines, automation, monitoring, and documentation, ensuring that security remains consistent and defensible. It also underscores the need for continuous improvement, recognizing that security is a process rather than a product. For learners, mastering Domain 3 provides the confidence to address the complexities of platform and infrastructure security, appreciating both the technical depth and the governance structures required. By unifying technical rigor with operational discipline, Domain 3 ensures that cloud platforms serve as reliable, trustworthy foundations for applications, data, and services in an interconnected world. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.